Slider initially start at 0 and slide all the way to 100 and slide all the way back. And we want to go at about 20 counts per second. Okay? And then when the go button is released, we stop right where we are, and then go button press, it continues from there. Okay? Pretty simple to think about, but you'll see it's just not trivial to program that. All right? So here's kind of the list. So tell me, what are the different modes? So can you guys team up into pairs of 2 and talk about what do you think the modes are, the states. We call it states because we're doing a state machine. What are the states? What are the modes or the states that the program is in different locations? What are the actions that it needs to do? And what are the transitions? When does it go from what transitions have to happen before I jump from one mode to a different mode? Okay? Alright, so I'm going to give you about 5 minutes to kind of talk that through. Pair up with a teammate. Bring this back up.
Where it starts, right?
Well,
it starts at 0. That's the first.
And then once it reaches,
yes. Well, the first thing, like, it'll be
transition
doing nothing.
Right, that's what I'm saying. Starts at 0 doing, right? Okay. And then there's a transition to state, right?
Yes.
Where it's moving from doing nothing to when the go is pressed, it moves up 20 counts per second. It's a moving state, right? Okay. Okay. Is changing a direction something that happens, or do you have to stop? Hold, reverse.
Right.
Is that 3 different states?
Yes.
Okay. And then it goes 20 counts per second until it reaches.
So is there a forward or backwards?
They're always sitting in there.
Oh, those actions.
Right.
So for an action, go forward.
Yeah, going. Yeah, because okay, so the state is just moving.
Right. Yes.
So the states are moving right, moving left. Yes. And then the actions are how fast it moves.
No, it would be like if one is
One
released,
thing,
then
I can go
Do you have any students? Did any students know that this was going on?
No.
How many kids do you have?
So we want 15. We have one student who comes back. He's did a couple years ago. He keeps coming back. Maybe 5 kids so far. Shoot, 15. For all the teachers just class and all of them. Miss Terry, she has a couple kids in computer science. So that's my goal, is to go through all the computer science and recruit from there.
Yeah. The hard part is that still that you're not going to IT kids because they're not going to take computer science because they're going to make something from that process. Just TOK is probably going to apply it for so you're not going to get that 200 kids.
Well, the problem with that too is I find that the kids who are the really bright kids, they're kind of doing other stuff already.
Yeah, but some of them are still willing to do it.
Okay.
I mean, I have at least one that would be willing to do it, and I might be able to pull in a couple more. But so I have one that was like, yeah, all about it. But
Okay. Can I be here?
yeah, she's a sweet.
So, yeah, we find that it's girls look out for always got one playground.
Mm-hmm. Yeah.
What days came on your paper? Once we started, we tell
Yeah. And there's nothing that making me not available except for that I have a 2-year-old and a 6-year-old. So, because because it's 6 weeks, right? Yeah, so I'll talk to my wife and see.
Okay,
how much
so,
it is, but I'm
what
thinking
have we
that
got so far?
I can certainly check in
So
every day.
what,
even if
what are we
get
thinking
get
are
a
the
task.
modes of the program, or the states that it's in?
So I could
What do
probably
you got?
do
Something?
an hour every day and more on Sundays. So, but
Yes,
When it has to, when it kinda has to go or back around, when it gets to 100 and has to go back to 0?
okay, so, so you're saying when the needle is moving this way,
Yeah.
moving that way,
I'm not
would be a
going to
mode?
Switch it.
Anybody have a good name for that? What would you, do you have like a one-word name?
left.
Left, okay. Do we have a left mode? Any other modes?
Right.
A right mode? So we're moving the needle right, or moving the needle left? Any others?
Stop.
Nothing, right? Stop. We usually we're gonna call this idle. When there's no expectations, you're just, your expectations are just stay where you are, stay where you're at, right? So that's kind of our three modes, okay? And we'll get into more complicated ones. If you think of a vending machine, how many different modes in a vending machine? Or if you think yourself as driving, getting in your car and driving, what are all the different modes where you're trying to accomplish something? So how about actions? What are the actions that we need to do to this slider? Yes,
Started.
pardon me?
Start.
Start, okay? How would you, if I said, okay, start, what would you do that slider?
Let's go.
Press the go, alright? What would the slider do?
Start moving whatever direction it was going in before.
Okay, start moving, right? So move right and move left. And always in our list is we're gonna just have a no action. Okay? Now, transitions. When do we transition from doing nothing to going left? What thing has to happen for me to say, okay, I'm idle, and now I need to transition to going left state?
Go gets pressed.
Okay? So if my go is pressed, and I get to 100, so I'm going, your left or mine? We're going right. When we get to 100, what do we do?
We have to go back
We
left.
have to go back, right? So we're transitioning from the right state, right? Moving the needle right to moving the needle left, right?
Yeah.
So what is that transition? When my slide is
It's at 100.
equal to 100, right? Okay, and then on the same way coming back, if I come to 0, right, and I'm in the left state, I'm moving the needle left, I get to 0, I see that I'm at 0, I need to transition to the go right state, okay? And then we transition from any of these states back to idle, when what?
Go is unpressed.
When the go is false, right? Okay, so I wanna caveat that when you're trying to solve a problem and you need your robot to go through a process, okay? Writing these down is good, and you're not gonna get them all right, and you're not gonna get these as granular as you need them to be. That's gonna come through a kind of an iterative process. So you start out with your best guess of what you got, you start to build your state machine, you move into coding, and then you keep thinking about it, right? You're like, okay, there maybe need to be more left states or more broken down states, and I'm gonna add to this, problem later, and we're gonna break our states down into a little more granular, okay? So how do we wanna diagram this? So what I wanna show you is just kind of a basic, called a mealy state machine, process to kind of break down our state's actions so that we can see the flow of the program and when we transition. And then, later we'll show you how to kind of create that in LabVIEW. Alright, so first thing we do is we create circles. So we always come up with a start state and a shutdown state. Alright, and then usually circles, call this idle. Left and right. Okay. And we go back to our requirements. One of the requirements is we initially start the slide at 0, okay? So I'm going to use blue for my transitions and orange is going to be my actions, okay? So start, we go immediately, we're going to jump to idle. There's no transition, no condition, I just immediately go to idle no matter what. And the action that I want to do is set slide to 0. Okay, so I'm in the idle state. And to transition from idle to the right state, what was the condition? What condition do I need to look for to tell me to transition from idle to right?
When go is pressed.
When go is pressed, right? Go is true. Alright, and then do I do an action here? So we always, oops. Do we do an action? So we want to do our actions always on the transitions, never like inside the state. So do we do an action from idle to right? Is there an action that we need to do?
20 counts
There
per
doesn't have to be, but do you see an action that we're gonna have to do?
20 counts per second? Is that an action?
So you wanna add increment 20. Okay? And the other transition, there's always a transition where we transition back to ourselves. Okay? So if I'm in the idle state and I wanna come back to the idle state, what's the transition for that?
When go is false.
Correct. If go is false, I come back to the idle state. Now, is there an action that I do? No, right? There might be, but in this case, there's not. All right, so I'm in the right case. I can either transition to the left case, or I can transition back to idle. Okay? If I'm in the right case and I transition back to idle, what is the condition that tells me I need to transition back to idle? So I'm moving right, and all of a sudden I want to go back to idle. Yes? was false. Okay, so I'm in the right case, and I transfer to the left case. So moving right, transferring to left. What is the condition?
The counter is equal to 100.
Sorry, my slider is greater than or equal to 100, right? We transition to left. Go to left to right. What's my transition?
The slider is less than or equal to 0.
And left to idle.
And go equals false.
Okay, let's see, did I miss any? Oh, left. Left back to left, and right back to right. So if I'm going left and my next state is left, what's the transition? Slider going left, that's your left, right? Slider is greater than 0. And here the slider is less than 100. Okay? So, like, that's not becoming trivial, right? There's a lot of things to think about there, and a lot of things to kind of implement. So, if you can imagine a more involved shell, say you got a robotic arm, right, that has maybe 2 or 3 joints to it. You need to move the arm over, move the arm down, pick something up, move the arm up, and slide it back over, right? Even that is kind of, so you can imagine the state machines get a little bit big and wieldy, but when you're in the code, you're trying to get it to work, it's always nice to be able to go back to a diagram and say, I'm working on left, and then just think about what are the things that make me leave the left state, right? Well, I either gotta look at the go button, or I gotta look at the slide button and make sure it's greater than 0. So let's finish the actions. So if I'm in the right mode, and I come back to right, what action do I do before I come back? So I'm moving right. My condition is my slider is less than 100. What action do I do?
Increase the slider.
The increment, right? And then the same over here, we're gonna decrement the slider. Okay, any questions? We're gonna keep going over this. This is really important to be a decent software programmer. To not only know the syntax of the language, but to understand kind of the design process. All right, so let's go over kind of a basic. Everybody's familiar with a Coke machine, okay? So what kind of states would you? We're not going to go through this entire thing, but what kind of states would you think would be in a vending machine? Yes.
Would there be a separate state for every single slot that you could access in the vending machine?
Slot as in like each where each pop is.
Yeah.
You could do that, right? So, yeah, there's not necessarily a right or wrong answer. It's either really granular where you make a lot of states, and you can see the more states you have, the more transitions you got to think about. But if you make them too general, then your state is trying to do too many actions. So it's trying to find a balance. So that's one idea, right? A state for every slot. And those states, what would they be doing in each one of those states? Pardon me?
Or it would just be,
It's okay.
doing whatever action you need to do to drop the setting.
Okay. So that'd be some of the actions, right? Any other, other states would you think a vending machine might have? So what kind of modes are it in? So one is obviously idle, it's sitting there doing nothing. That is a state, right? And then what would be a transition to another mode? Money being inserted, right? Oh, I see a quarter. So now what state would you put the machine in?
Maybe like a counting money state.
Okay, counting money, right, making sure that the money state, okay. So now in that state, what actions would it be doing? In the counting money state?
It would be like trying to count the money to see how much money has been inserted in the machine.
Okay, right. So that's kind of its goal, right? And so then what's the transition to another mode? What would be another mode that we transition to?
A button for when the soda is being pressed.
Okay? Good. So like vending or getting the product, right? That would be the other mode. What is the transition from money, collecting money or counting money to vending, grabbing the product? What's our transition there? Yeah,
Well, first you have to confirm that you have like enough money put in, and then they have to make a selection.
okay, so two conditions, right? So enough money and the button's pressed, a button's pressed, right? So now we transition into get product. If the button is not pressed, or we don't have enough money, what state do we go back to? What state do we go to? Stay, yes? I'm already telling you the answer, right? Yeah,
Well, if you're transitioning from, so you said some of the contingencies about going from the non-counting state to getting it. Wouldn't you also have to verify that whatever numbers are being pressed are valid?
oh, that's a good one, right? So that, we add another and there to say, to make sure product available, right? So you'll see that there's gonna be lots of ands, or this or that, either one, we can move to the next state, so, yeah. And, like I said, it's an iterative process, you're going through it, and you're getting there, and you're like, well, what about if this happens? Oh, then we gotta go back to our diagram, we write in a new condition, and we see if it takes us to a new state, right? So some of the actions that our vending machine does. So we already talked about counts money, increments our bank or our money. It goes and gets our product, right? Yes?
Returns the money.
Turns money. Any other actions you can think a vending machine's gonna do?
Am I asked to give you the soda or the Coke?
Okay, so some kind of interaction
Yeah.
through the user interface, right? Blink a light or something like that, right? So here's one person's idea of what a state machine, a Coke state machine would be. So they broke it down. They're waiting for an event state. And then each time a certain piece of coin is put in there, they move to that state. And you'll see nickel is put, then we go to the nickel state, and then we look to see if the money is equal, this is our action right here, our money equals money plus 5, right? We've incremented the money. And then there's a transition, dispense, and then our Coke product, right? So there's not one way to build a state machine, but thinking it through will make it easier to program. Here's, one of maybe a drive system for a remote control of a robot. Where we go into different read states. So sometimes states and actions will seem redundant. So we have a move right action, and then we're actually in an act state as well. But, so try and keep in mind that actions is something that the program is a verb, it's actually doing, it's going and doing, right? So move right, we physically go in and we increment the slide, okay? But the mode that we're in is trying to accomplish moving the slider right. Okay, so a little bit different, but the reason we keep them separate is you may wanna do multiple actions in a right state. So I may wanna not only move the slider right, but I may wanna check sensors as well and do a bunch of other actions. Alert the user, right? There could be a whole list of actions that I wanna do when I'm in the move right state. Okay, so, does everybody have LabVIEW? Let's, and everybody open a blank VI. Okay, how many people have not touched LabVIEW before? Never touched LabVIEW? You? Okay. You have a computer? Okay. Okay, so, very quickly, LabVIEW is a graphical programming language. We always have 2 panes per file that we're trying to save. We have a front panel and we have a block diagram. Okay? Familiar to everybody? We are going to go to our front panel, which is our gray, and we're going to right click and you're gonna put a slider down. So it's gonna be here in the numeric palette. And if you go over to the handles and drag it, just make it a wide slider. And set it from 0 to 100. And then I want you to grab a boolean and make a go button. All right, and then we're gonna put a vertical slider right here at 50. So put a vertical slider right there.
Where do you get the Boolean?
In the Boolean palette, so there's a numeric palette, Boolean palette. And I'm gonna label that from 0 to 10. All right, so this is gonna be kind of our class project. I mean, if you're able to program this, that's kind of my goal by the end of the day, that everybody will know how to program this, okay? So, similar of what we just went through, but I added another slider. So, mechanical team added another mechanism in your robot, okay? And what they ask you to do is they ask you to increment this slider, it gets to 50, and then stop And then this slider goes down, and then back up, and then it continues from 50 to 100, comes back, stops at 50, down, up, and then back to 0, and repeat, as long as that go button is pressed. Okay? And this is so typical, right? I mean, they're always adding stuff, or they're always taking stuff away. And you always gotta go back, modify your state diagram to do that. So, first thing I want you to do is, we have a really good start here. I want you to write, to build the state machine. So list out your states, list out the actions that you think you need to do, list out the transitions. How do we transition from one state to another? And then try and draw a state machine. And we'll take about 5-10 minutes to do that.
So up 50, and then 50, and then down, down, or down, down.
Go ahead.
I don't. What was the challenge?
So we have a slider here that goes from 0 to 100.
100. Okay, that's not the right amount. I did the same thing. So. Yes, please, thank you. And then this is 0 to 50. I got.
Yeah, so you put that right about at the 50 mark. Grab it.
Oh, okay. Can I move it this way?
Yeah, so you gotta look for the, you watch the tools. You see the arrow tool?
Yeah, I got it.
Click,
Good.
you should drag.
And then at the 50?
Yep.
Okay.
Alright, so then we want the slider to go 0 to 50.
Okay.
Stop. And I want this one to go, so label that 0 and that 10. So double click here.
Yep. Alright, so, and then, so 0 to 50, and then up to 10.
No, start 0 to 10, so just label that as 10. The top one is, or 0, sorry.
Oh, okay, 0 to 10, got it. And then, got it.
10.
And then up to 50, up to 10, up to 100, back to 50, down to 0?
Correct.
Got it. Can I have that paper, piece of paper? So I can write down what I just wrote.
Yep.
Yeah, when it gets to 50.
0 to 10, 10 to 0,
Correct.
50 to 100, nope, 50 to 100.
Huh? Okay.
50, 10 to 0, 50 to 0, okay.
Okay, so it's very important in that folder I gave you, there's links to all kinds of videos of all the other people that are trying to show you how to do LabVIEW, okay? So please practice going and becoming familiar with the environment, learning how to do it. And so we're gonna touch on this stuff and kind of keep moving through, because we want to talk about how do we build robot code eventually get there. Okay. So the main structures, two of the main structures that we use in LabVIEW is called loops. This is how we do things over and over and over again. And loops are also graphical. So this is a while loop. So data flow dictates, we wait for all our inputs to come in. We run everything inside of this code space until everything is complete. We look to see if this boolean is set true. If it is, we're gonna run it again. If it's set false, we stop the loop and we release all our outputs. Okay?
Yeah.
This is do until this is true. So we keep doing the loop over and over and over until something says this true. Something says that true. for loop will run a given number of times, so you put that number, that, either through constant or terminal, you tell this loop how many times it's gonna run.
Oh, okay.
Yes,
So a function can work within a loop even if it's not actually connected to anything?
correct. Correct, we can plop a function in here, and as long as it's not, doesn't have dependent inputs, doesn't break the VI, it will run. A while loop looks like this, this would be its flow chart. We wait for, if the condition's met, no, we run the code over, and then once the condition's met. You can switch this to say stop if true, or continue if true, so that's the continue if true icon. Terminology, this is called the iteration loop. That releases a number to tell you how many times that loop has been run, okay? I for iteration means that it starts at 0. So the first time you run this loop, that I will be 0 and counts up from there. Computer science people like to not waste numbers, so we start at 0. This is called the conditional terminal, and this is called the iteration. So this is what you think of as a control. It delivers data, and this guy is like an indicator, it receives data. For loops are used when you want to run something a known number of times. We'll talk about arrays, but for loops and arrays work really well together. So if we wanted to build a list of like 45 random numbers, we would set our for loop to 45. We'd write code to generate a random number, and this little box here with the brackets tells you that it's building an array. So every time we run this loop, it creates a new number and it adds it to the list. And then when the loop is complete, we have an entire list of our 45 numbers. If these little brackets are not in the tunnel, then it will just send the last value. So if this loop ran 45 times and was done, we'd only get the last value. Because you're looking, the tunnel should tell you if you're creating an array or if you're using using the last number. Creating a loop, we go to the palette, select loop, and then we draw a box, and it will engulf any code that you've wrapped around it. Tunnels are like the inputs and the outputs. Okay, so again, once you create a tunnel, that creates a data dependency, and this loop can't run until that data becomes available. And it will not release this data until this loop has completed. Okay, so if you're running a loop and you want to constantly know what the iteration is, you need to put an indicator inside the loop so that this data will be pushed to the indicator every iteration, okay? If you have it outside here, you won't see what the iteration is until the loop has completed, right? Due to the laws of data flow. So a for loop, you can also add a conditional terminal to a for loop. So if you have a for loop and you set it to 100, but for some reason you only want it to run 10 times, like a maximum of 100, but it could stop at 10. You can right click on the little N here and say add a conditional terminal, and it'll either stop if this is true or if we've done it up, if we ran that loop 100 times. The count terminal, that N terminal has to be an integer because there's only whole numbers in looping. So here's some examples in your FRC code where you probably see a loop. So this is setting an angle, a servo angle for our robot. It had an arm. You ask, can we make the arm move up and down? So this code here basically creates the servo object, and this constantly sends through this loop runs constantly, sends data to the set servo arm, so it's constantly setting the angle. And then once the loop stops, we close, we get rid of all the information about the servo. So you'll notice there's several things in parallel in this loop, like I talked about before, where this is in parallel with this, in parallel with this, right? So there's no way to know when these happen, but we have to wait till everything inside this loop is complete before we move on and try to either leave or loop again, okay? So we put this timer in here, like I said before, and it sits there and waits 50 milliseconds and then releases, waits 50 milliseconds and then releases. So this, and this happen pretty quick, in like milliseconds, microseconds. And then everybody's waiting for the slowpoke, the 50 millisecond guy, before we can move on, okay? So that limits that this loop will only update my angle every 50 milliseconds, okay? And you typically always wanna put some kind of weight thing inside of a loop, inside of a robotics code. Because if you don't have this in here, it'll run this loop probably thousands, hundreds of thousands of times a second, which is a waste of your resources. And this, although this thing is pretty awesome, it doesn't have infinite resources, right? And there's no reason to update the servo angle on an arm 50,000 times a second. So this would be a sensor, so that's kind of an actuator. This would be what a sensor loop would look like. Again, some kind of setup code to set the sensor up. We tell it that we want it to give us our output in inches, and we constantly are reading from the sensor every 50 milliseconds, and then we send it to an output. Okay, so a thing that we use a lot with loops is called shift registers. What shift registers do is a lot of times you want to know what was the last value that I just generated for the next iteration, okay? So for in this instance, we want to keep adding 2 to this value. So we need to know what the last value is when we come back around again. So what a shift register does is it puts data in the shift register, and then if the loop goes another iteration, it takes this data, puts it over here for the next iteration to use it. If this loop stops, it takes the data from the shift register and sends it out. So I have a video that explains shift registers. Turn the volume back up. Put this black on.
Store and pass data from one loop iteration to the next, and will be able to predict the After completing this module, using shift registers, you will be able to recall how shift registers store and pass data from one loop iteration to the next, and will be able to predict the correct value of a shift register at different iterations of a loop. You'll learn how to use uninitialized, initialized, multiple, and stacked shift registers. Sometimes when you program with loops, you need to access and use data acquired in a previous loop iteration. For example, if you need to get the average of several temperature readings, you would need to use the value from several previous loop iterations. LabVIEW uses shift registers to store and transfer any type of data, such as numeric, Boolean, or string. Shift registers appear as a pair of terminals directly across from each other on the vertical sides of the loop border. When a loop iteration completes, the shift register terminal on the right border transfers data to the shift register terminal on the left border to be used when the loop iterates again. Let's take a look at an example of using shift registers with a for loop. The for loop shown here is configured to run 2 times and add 3 to the value passed from the shift register each time. Because the left shift register is not initialized, it has a value of 0 before the VI runs the first time. During the first iteration, the VI adds 0 and 3. The value of 3 is passed to the shift register and used during the second iteration of the loop, this time adding 3 plus 3. After the VI completes, the value of the output indicator is 6. Because the shift register is not initialized, when you run the VI a second time, the right shift register holds onto the value of the last iteration, 6 in this case, and passes it back to the left shift register. So the second time the VI runs its 2 loop iterations, the value of the output indicator is 12. The default value of an uninitialized shift register for a numeric is 0. For a string, the default is empty, and for a Boolean, the default is false. Take a look at this block diagram and determine what value is displayed in the output indicator when the VI completes.
Okay? How many times is this loop gonna run? Is this a for loop or a while loop? A for loop, right? That's the little flippy page or whatever, that's how you know it's a for loop. This little icon, this little flip or whatever tells you, and then the N to tell you that this is a for loop. So it runs a predetermined amount of times, okay? And then we wired the N 5 to the N, so this loop is gonna run 5 times, okay? So go through that in your head, run that loop 5 times and tell me what the output is gonna be. Anybody got an answer? 15? Anybody disagree with that? Correct.
What value is displayed after the same VI runs a second time?
Okay, so we ran it once, and our shift register is uninitialized, which means that what? What does that mean? What's the starting value gonna be here? Was our last answer? 15, right? There's nothing to tell it to change this data, no input coming in, say started at this value, so it will stay at the previous value, okay? So we're running this VI a second time, we've already ran it once, and we have 15 in this shift register. So we're gonna run it another time, a second time, what's our value gonna be? Anybody disagree? Correct.
If you want the loop to start with the same value each time the VI runs, you can initialize the shift register with a control or constant to reset the value for the first iteration of the loop. Here, the shift register is initialized to start with a value of 1 when the loop runs the first time. This means that when the VI completes, the value displayed in the output indicator is 5. Take a look at this block diagram and determine what value the output indicator will display after the VI runs 1 time.
So this time we're initializing the shift register. Every time we run it, the first item in there, shift register is 3. In the back, do you have an answer?
Maybe 7?
7? Correct.
What is the value of the output indicator after you run the VI a second time?
So a second time, again, we're using 3, so value doesn't change.
7.
Correct.
A loop can contain more than one shift register. If you have multiple operations that use previous values within a loop, you can use multiple shift registers to store the data values from those different operations. Notice that the shift register pairs are directly across from each other on the edges of the loop. The value of a shift register is stored and passed to its paired terminal directly opposite it on the loop. Here we are keeping the value of the add operation and the multiply operation. The first iteration of the loop stores a value of 2 in each shift register, and then forwards those to be used in the next iteration.
Everybody understand that? So we'll use shift registers, in the template I'm giving you, we'll use shift registers to hold all the data that loop cares about. We'll put it in a cluster, and then the loop will continuously run this loop. We'll keep walking through our different states, and we'll hold the latest data in a shift register so that the next iteration that data is reused.
A loop can also contain what are called stacked shift registers, which retain values from multiple previous iterations. A loop can contain more than one shift register.
I don't want to talk about the next thing. We don't use them, and they're not that interesting. So it's shift registers, we kind of went through that. So how do we get a shift register on a loop? We make a loop, we right click on that loop, and we just say add shift register. It will create 2 shift registers, it will create them, and they'll be black. Until you define what kind of data type that shift register is going to use, it will be black. So you do that by either wiring this side, this shift register, or you wire a starting value. So another thing you might see is a item that looks like this. This is kind of like a standalone shift register that can sit anywhere on a block diagram. It's called a feedback node. But all it is a shift register that is kind of standalone. So it doesn't have, so you can use this iterative data transfer standalone like this and like this without needing to be inside of a loop. So what do we use those for? We use these a lot to detect. A lot of time when you're pushing a button or you're using joysticks, you don't want to know if it's on or off. You want to know the transition from off to on. You want to do something or fire something when you see the transition. So if they push the button, you want to fire a solenoid. You want the solenoid to go on and shut off. And you're waiting for a rising edge. So to do that, we look at a button and we look to see, is it currently high and was it previously low, right? That shows us that we have a rising edge, that we've seen the transition. And then that output would be true for the split second until we come back and read it again. That's one place where you use a feedback node. Another is if you're looking, hey, did my data change? So I'm running and I'm reading my data, I'm reading my sensor data, and has my data changed? And I want to create a Boolean that flags or goes high if the data changes. So you'd say, here's my current data, and I've stored my previous data in a feedback node. Are they different? And we say true, and then we go do something. The sensor data is new. I need to go adapt or slow the robot down or something. All right, so let's play with loops. Let's open a blank VI. You guys still have the slide VI. Did you save your slide VI with your 3 slides on, your 2 slides on it? If not, quickly make another VI and put your vertical and horizontal slide on it.
That was it, right?
Is everybody there? Okay. So I go to my block diagram. Now, I want to display a slide value. I'm not controlling this. I'm the user or whatever is not controlling this. So are these supposed to be controls or indicators? If I just want to display the slide value. Indicators, right? So if I go to my block diagram, and you may or may not have this, but my slides are controls, right? So I need to change them to indicators. So the magic right click, and we can say change. You can change any control to an indicator, or any indicator to a control, or anything to a constant, or any constant to anything else. So you right click and you say change to indicator. So now those values are indicators. They tell me what a value is, okay? So change those representations to I32s. Change those 2 slides to I32s.
You want me to?
Okay, so just put those off to the right. We'll get to those in a second. So we are going to start building a state machine. So the first major component that we've learned about so far is a loop, right? We're gonna continuously loop, we're gonna continuously jump through states. Okay, so let's put a while loop right here. So our while loops are in our structures palette in the top right, and then the second one over, first one down is the while loop. And you'll get a little box cursor, and you just draw a box, and a while loop will magically appear. Okay, we need a way to stop our loop. So we're gonna make it easy. We're gonna create a control off of our conditional terminal. You're gonna go down here and right click and say create control. And then we're gonna add a shift register. So I want you to right click on the border of your while loop and say add shift register. added 2 of them, so add a second one. Alright, so go down here to your, create a constant off of your slides. And we're gonna use that as the initialization. We're gonna create a constant. I'm gonna break the wire. And we're gonna initialize both of these shift registers at 0.
And make it black. Delete the wire merge.
What time are we supposed to be done, do you know, remember?
4.
4? Okay. Alright, so just watch me for a second. I'm gonna kind of go through the rest of the steps, and then I'll let you guys code. So I'm gonna bring my indicators in here. We're just gonna do slide 1 for right now. Okay? So, you know, if I want my slide to update during the loop, I need to keep it inside the loop so it constantly updates, right? So I'm gonna take the previous value of my slide, I'm gonna increment it by 1, and I'm gonna put that value back in the shift register, and then I'm gonna display it, okay? So I'm gonna find an add 1. And I'm gonna put it back in the shift register. And I'm gonna display it. So I'm gonna display it before I add the 1, because I wanna read every value. Right? Now you see, if you watch, if I run it, oops, I'm broken. The shift register is not, that's right. If I run it, oops. Gotta make sure it's in my computer. Make sure this is set to my computer, so it runs in your PC, not in your target. Boom, right? Happened instantaneously. Why? Because I didn't slow the loop down. So I'm gonna just show you, if I put an indicator on this is my iteration terminal, this is the value. Remember, it starts at 0 and it tells me every time that loop is iterated. Watch how fast that increments. That loop is running almost 10 million times a second on a PC. And it'll run faster on the RT, because the RT will run a little bit faster. So there's no reason to do that, so I'm gonna put a timer in here. We're gonna look for a wait timer, either quick drop that. And we're gonna slow this down to I'm gonna create a constant and make it 200 milliseconds. Okay, so now I have 2 things going on. I'm adding the value, and then I'm waiting 200 milliseconds before the next loop iteration goes, right? So you'll see that one will run much slower, and I'm incrementing my slider. Okay, so write that code, and then we'll go on to the next thing. Try not to copy, try to think through that. Think, okay, I want to increment my slider, I need to use the shift register. Go ahead.
I might have missed a step, but when I tried to create a constant, I'm not sure if that was figured out.
So you have a shift register and it's black, meaning where we have to create constant off a node. You just need a constant to where you do it.
bundle by name.
Right.
Yep.
So then.
Right, then it should.
And I could put that in. It should show up here as an option.
So you need to wire your cluster
okay.
to that arrow,
Okay.
and it will give
Okay.
you all your options. Now,
And
go
then
in the
I
middle to the finger, show the finger tool. So we got an off click you've selected already.
can- Okay, got it.
There.
And then I can
There's
choose
your
horizontal.
select.
Got it. Thank you.
Why are we not just connecting this to here?
And then close it on.
Or just like
Yeah.
keep it looking nicer. I mean, you could do it,
Um,
the slide one like after the curtains right there. But like, I think for organization purposes, just like doing it again, that makes it easier to comprehend, you know what I mean?
Later, this is gonna be part of key structure. We may or may not do it, right? We may or may not add, but we still wanna display the horizontal slider, even though we may not operate on it. Okay, wire the middle terminal first. Here you go.
No, that's wrong.
See the middle, the center one there, center terminal, wire that first to the cluster.
Like this? That's right.
Show me the wire
And
tool.
then he added another.
Go to the center terminal.
Is that a vertical wire? Is
That's
that the
not the
other
center
one, or is that
terminal.
the single?
Center terminal. See, there's three right here.
What's the last piece?
Go to the center one. Show me the wire tool. Center. Higher. Higher. There.
What does that one do?
This one. See now it gives you the list. So you go in here, you see the finger tool.
Yep, yep.
Cover in the middle. Finger tool. There's your, so select horizontal. Yep, and then now wire the output back into the cluster. Break your wire. And then delete that center section. Okay, so run it and make sure it works exactly the same as last time. Okay, save this because we're gonna come back to it.
This section proposed in, so, this right here is like a here, because this one is going to be key structures, so just.
Okay, so, we'll come back to that in a bit. Other thing we talk about is timing, two types of timing in LabVIEW. One is, blocking timing, where we're blocking everything inside that loop from running until this timer completes. And then we run again. And then we have, terminology is. This function reads the current time, the current clock time, and you compare it to a previously acquired clock time, and you subtract the two to say how much time has elapsed. So this is kind of like an elapsed timer, okay? Doesn't stop the loop, we just keep asking, is my time up? Is my time up? Is my time up? Right? For the elapsed timer. So the time when you want it, say you're driving a motor or you're driving a robot and you want it to drive forward for 2 seconds, okay? We don't wanna turn the driver on, turn the output loop on and lock that loop for 2 seconds and then come back and turn it on to 0. You wanna constantly be monitoring, because we also may have a sensor that says when we've reached something. So we either run for 2 seconds or we see the sensor. So we would acquire our start time before we come into the loop, and then every iteration we look at the current time subtracted from the start time, tells us how much time has elapsed. When that time is greater than 2, we shut the motor off, right? So this is better for that situation. This is better when we're trying to slow a loop down, it's running too fast. Yeah, question?
So this is something you probably use in Congress, right?
This might be right. When you're trying to time something for a certain amount of time, but you want the loops to keep running, you would use this method, right? When you're trying to slow a loop down, then you'd use the blocking method. Some ways to do this are, this is another way, this will give you a millisecond tick count. And that way it will give you the actual clock time within, I think, microseconds. So one way to do it initially is say my current time plus 5 seconds. When my time is greater than that time I calculated, then stop the loop. You can do it that way as well. Or you can do it this way. So lots of ways to kind of do that, but this is used a lot in timing. You always want to kind of get a start time and then compare your current time to see if you've timed out. Okay, we're going to talk about arrays, and we're going to go quickly through arrays. Arrays are a group of so we're talking about the 2 ways to group things together. One we talked about was a cluster, and another way is arrays. So arrays are a group of identical items, okay? So this would be, on the front panel, this is what an array of booleans would look like. See, every one of these is identical. This is an array of numbers. So arrays contain numbers, and the way to identify an item inside of an array is to use what's called its index. And because it's CS, we start with 0. So the first item in an array is always 0. And then you count up from there. So if I say, give me the first item in the array, your index is 0, okay? And really what index means is if you think of this as the first item, the index is think of it, the index is this line, right? So this is the 0 point of the array, so 0, 1, 2, 3. So when I say index, I'm really referring to this line, the starting of that value. You can also create a 2D array. We don't deal with them too much, so I won't go into them. On the front panel, we identify the item by the little index marker there on the front panel. And there's lots of array functions. This allows you to build an array programmatically, add items to an array. What else we got? We build 2D arrays. This allows us to pull elements off an array. So I have an array here, 2, 8, 1, and I say I want to index that array, item 0. What item am I going to get off of there? What is item 0 in that array? 2, right? Index 0, 1, 2. I'm going to have you guys study the array functions. If you need, there's an array palette that you'll notice, you right click on there, there'll be an array palette that has all these array functions. So if you're looking to manipulate, delete, add items to an array, they're all in that palette. So here's a common thing that we use an array for. We'll initialize an array with all zeros, 5 items with all zeros in it, put it in a shift register, and then I will get a new value from my sonar, and I will put that value into the array, throw away the old value, put in a new value, and then I will take an average of that entire array to see what my average value is that my sensor is delivering. So that's one way you use an array. The one that we most common use is, we did this, right? This is our joystick. We get values. This is an array of all our axes, an array of all our buttons, and an array of all our POVs on our controller. And we pull off, by index, we pull off the axis that we want to look at and evaluate. You can also use arrays with buttons. That's the code to write to make a toggle. If you want to make a button to work like a ballpoint pen, where you push it and it's on, and you push it again and it goes off, that's the code how to do that. So auto indexing. So arrays and for loops work very well together. So a for loop, we talked about that little bracket tunnel, will build an array for us. So this will build us an array of six random numbers. And if we right click on the tunnel and you can say use last value, it will only give you the last value. So it'll run 6 times, throw 5 numbers away, and only give you the last number out. You can also make it conditional, whether you put it in the array or not. So in this instance, we have an array of numbers here, and we only put numbers back into the array going out that are less than 5. So you can see that here's the starting array, and we threw away, we rebuilt a new array, but only with numbers less than 5. We build 2D arrays. One thing to note with a for loop is if you wire an array into a for loop auto indexing, it will try and run that many times as there is items in the array. So if you have 5 items in the array, this loop will try to run 5 times. Okay, so that's why for loops and arrays work really well together. But for loops are lazy, so if you give it multiple options, so I'd say this guy wants me to run the loop 10 times, this guy wants me to run it 15 times, this guy wants me to run it 5, it will take the lowest number and run only 5 times. Right, so just be aware if you are trying to have a loop run different numbers. It'll always take the lowest. Clusters. So clusters, unlike arrays, it groups numbers, it groups items, but they can be different. So you can have numerics, booleans, strings inside of a cluster. And a cluster is a way to kind of contain data that all pertains to a certain function or subsystem. So you may put anything that has to do with the drive, you would maybe put that in a cluster. The speed, the shift position, the XY values, something like that, you kind of typically put that in a cluster so you can have all that data stay together. Clusters versus arrays. Again, arrays is single data type, always must be the same data type, but you can vary them in size. Cluster can do mixed data type, but they have to be a known size at the beginning. And we'll go through creating clusters. two ways to get data out of clusters that we practiced. One is unbundle by name, and one is just the unbundle. The unbundle by name I recommend that you always use because it helps self-document. This gets a little bit harder to read. So use unbundle by name when you want to pull data out. Kind of went over that. There's the bundle function. This is how we put data back into a cluster using the bundle by name or the bundle function. Again, where I see a lot of problems is people, if you're doing a bundle by name or a bundle, always wire this middle terminal first, which will set the cluster, which will set the node up, so then you can select and wire the correct ones. So you can change this value to any of the other values by just hovering here and using the finger tool, click, it'll give you the list, and you can select. Okay, so LabVIEW allows you to take your clusters and your enums, we'll talk about in a bit, and make them specific control files. And the reason you want to do that is say this is the data on a timer that you're using, and you're using it maybe in 2 locations. And if it's tied to a file, a LabVIEW file, then both of those systems are pointing and looking at that file to see what the data is supposed to, what the structure of that cluster is supposed to be. And if you decide, oh, we need to add another Boolean indicator, say for overtime, you can put that Boolean indicator into the cluster, save it and update it, and then both things that are using that will see the update, okay? If you don't do that, if you just create a cluster, throw things in there, and it's shared everywhere, if you update it one place, it doesn't necessarily get updated everywhere else, and your code breaks everywhere. So we have a very strict rule that if you create a cluster, or you create a new enum, that you make it a type def, you make it a file. So that if it ever gets updated, everything that uses it knows that it's updated. This is for my team. We beat this into them. You have to make, when you're making a new cluster, make it a type def, okay? So let's learn how to make a type def. So we're going to take and make a cluster of our slides, okay? So does everybody still have this open? Okay, so bring up a cluster constant, control space cluster constant. Just cluster, I think. Control space cluster. Okay, and so what you get is just kind of a shell. We're going to take our slide, we're going to drag it into the cluster till you see dotted boxes. Like so. And then we're going to right click on the border and we're going to say auto sizing size to fit, so we'll auto size. And then we're going to put the other slide in here as well. horizontal and vertical data. And I'm gonna bundle it by name. Like that. So what I've done now is I've separated this loop's horizontal and vertical data from how I view that data. So I can change this cluster to view that data any way I wanted to, and it's not the slider data, it's the horizontal and vertical data, right? Called decoupling, right? So now this data can be viewed or manipulated inside this loop anyway, and we don't have to worry about how it looks. We write code to show how it looks. So you're separating the look of it from the actual manipulation of the data. And maybe, or hopefully it'll become important why we wanna do that as we move through. Yes?
Do the constants of 53 and 0 have any sort of like bearing on how those are gonna function?
Good question. Yeah, only if so you can show I can show the, show the labels. So if I didn't write a slide value, then the output here would be 53. Because I say I start with this value as a constant, and then I only change the slider to value of that cluster, and then I write it out, right? Correct? So in this case, it does, but if I'm overwriting the slide value, then it overwrites that 53. Good question. Okay, so the other type def we're gonna learn is, that I want you to make, every time you make, is called an enum, okay? What an enum is a link, is a list of things, but they're numbered, okay? And, so let's bring up an enum, so control space, enum. And then you wanna right click in your enum and you wanna write set to visible items. Or edit items. Okay, so this enum that we're gonna create an enum for our states and our actions. Okay? This is gonna be a defined list of all our states from our state machine. And we're gonna create another one that's gonna be a list of our actions that we do. Okay? So do you remember the states? For each item in that list, create a state. So start with startup, a start. First item in the list should be start. And then we want an idle in there. And then you want an end, or a shutdown. And then the other states. So we want 0 to 50, there was a 0 to 50, 50 to 100, 100 to 50, and a 50 to 0, right?
What's up? One more second.
Start.
Yeah.
50, 50 to 100, 150. So that's for the horizontal motion, and then up, down. Okay, so same procedure like we did for the cluster. We're gonna right click, we're gonna say make type depth. And then right click to open the type depth. We make it a strict type depth. And then we save it. Call this your state. And then don't forget to apply changes. And then close. All right. So now we have a list of all our states. Let's create an enum with a list of all your actions. So we need no action, increment, and decrement. Just those three actions. Okay? So create another enum, label it actions. We want increment, decrement, and no action.
You make strict.
No, I didn't.
Right click in there and say edit out. No action. For the three items. Pardon me? No, state.
I know
This one should be.
obviously some, I know I'm on the state.
Oh, right, state one? Okay.
What?
Okay.
A little bit less, but just.
Right, so we want your state and your actions. You want those to be on.
You have to do the reverse.
So you say
So
down.
everything first, and then bring it. Because it's going this way, it's not making the result.
And you want to show the labels of them.
I think if you have, I feel like if you have a map of these, like, and I think, like, because I feel like your biggest reason is like just adding it on top.
And then you want
right?
to
I think that's really the only reason.
Hold on two items.
What would you have?
The control. So you have to keep up with the other control terms. So we have control up and
Right, but wasn't that embedded into the?
just drive.
Oh, okay, so it's just a driving analog. So you didn't have any arms.
We did, so we had to add arms. So
Oh, okay, that's the addition. Okay.
we had to look what arms do, like arms go up, cross open, close. Right.
I feel like if you had a good map of what you wanted the robot to do, and if, like, I feel like, yeah, they might not know how to do that,
now we get into, the most used function in LabVIEW called the case structure. So, if you know, this tool is probably the most important tool to learn because it teaches you how to make decisions. So we have a lot of decisions in this state machine that we gotta make, right? We gotta decide, things like, what's our next state? What actions do we do? What is our condition for leaving our transition? So a lot of decisions to make, and so we use these two tools to help us make decisions. So the select tool, we kind of played with that a little bit. That just, we bring in a true false, and we decide, use this data or use this data. And a select tool can work with any data type. So we can say, this for instance says use the current time or use previous time. This one says use stop motion or use the up motion, right? So the other one that's a little more versatile is called the case structure. And the case structure, think of it as like a deck of cards, and this little question mark on the case structure tells you which code you're going to run, which card you're gonna flip up and run that code. A case structure can work with true, false through a boolean, so you can bring a boolean into that question mark. And you have two cases, the false case or the true case. You can bring numbers into a case structure, so you can create any numbers, and what we use it for mostly is we bring an enum in there. And then we will have a code space for every one of our, we just created an enum for states and actions. If we run them into a case structure, we will have code space for every single one of our states and code space for every single one of our actions. And that's what we're gonna do next. So parts of a case structure, so up here's the selector label. You'll click on this little black arrow and it will give you a menu of every single case that you can choose. And then when you choose that, it will bring in the code space for that selected item. We have our selector term
the box.
the beach would
Those are the
probably
ones
be
that
Hook to the box.
Yeah.
And then
Yeah,
put that
that's what it is.
right? And now,
Yep, stop at the border.
Maybe they really have jazz.
Start here. Start there.
He already did.
Go to the border, release, then start from there. Slow down, watch for the wire tool. There you go.
it's broken after that.
There you go.
To be honest, it's to be honest, the turtle weird one fits her.
You missed.
Somehow she acts.
Yeah, slow down just a little bit. Give yourself another 2 seconds. Good, good.
Wire branch.
Right.
So I deleted the wire branch, and then I have
Go to
a
the-
spool.
Go to the tunnel, but don't go to the question mark. Just go to the outside.
Okay, go here, click.
Yep.
And then take
And
Okay.
then start from there,
That's
here.
and then come all the way
Here?
out, yeah.
Okay.
Watch for the blink.
I did.
Good. Awesome.
Did. And then like expand control.
Help
like
H.
Okay,
That help?
so this is going to be our case structure for our states, okay? So whatever our current state is, we will go to that page, all right? So we need to, from our cluster, we have all our stuff bundled up in here, we're gonna unbundle our state and wire our state to our question mark. So do that. Unbundle by name.
Inside or outside? Question mark?
Can you clean up?
Yeah, I was just gonna remove this rather than cleaning up, because cleaning up makes things easier small. But I was going to clean it up.
Yeah, well, you need more fly guy, the build it's a little slow, right?
Forget how much time this takes. I'm glad we didn't have 20 people, like you said we were gonna have. It's good.
Anybody struggling?
This is a team effort.
All right, it's supposed to be. All right, and we're gonna create a loop here around, remember we said this is gonna be one of our actions? What action is this gonna be? Where 3 actions are what?
Increment.
No action, increment, or decrement, right? So this is gonna be our increment action, so we're gonna draw, I want you to grab another case structure and draw around here, give me about the same amount of space, and make sure you keep the timer outside of the case structure. So go ahead and do that, create a case structure for your actions. And make space if you need to.
But you need
Yeah,
to wear
I can help you.
what
Unless you need,
Could be that we didn't.
No, I think
it may be that that's what it is.
get the,
I'll remember.
Okay, so that should
You
come
only do
up
like
with
this
names.
by itself here.
what are you doing?
So, I think you missed.
It's so long.
Broken, let's find out why my code's broken. So I click on the gray arrow, and it brings up my dialog box, and it says something's wrong with my slide VI. My tunnel is missing an assignment to the tunnel. Remember the rules of case structures? Is every single case must write to this output, okay? So how many cases is that? That's a lot of cases. So that's a lot of flipping wire, flip wire, flip wire. So LabVIEW gives us a shortcut, and it's called wire tunnels. So we will go, I will go to this output, and I'm gonna right click, and I'm going to say linked input tunnel, and I'm gonna create and wire unwired tunnels, and then I'm gonna tell it, this little icon says show me the source, show me where the start of that wire is. We click here, and you'll see it wired it, every single one of my cases got wired through. Alright, so watch one more time, and I'll do it on the actions as well. We're gonna right click on the output wire. We're gonna say link input tunnel, create unwired cases. And then we are going to select the start of that wire, which will be this tunnel to the left, and it will wire all of them for me. Alright, so go ahead and do that.
You cut off? Okay. Yep, that looks good. Yeah, now show me, is there any defaults? If you go to that little arrow. Yeah, default. Select that.
Oh. That one is up and down.
And then right click and say add every done.
Well, increment the count, correct, with increment the count.
Oh, yeah. So how?
So from 0 back to.
Right.
Or 100 back to.
How we can get from 0 to 10. I know we're trying to get there, but
What?
0 to 10.
So because you're out of linked input tunnels, every case it creates already wired it for you.
Yes.
So you have to do the same.
Increment, count 1.
Right, but how do I actually make sure that this then to vertical? Because right now it's horizontal, it's not horizontally, but now it's
Good job, good job. You guys got it?
I think so.
Okay.
So you go. And that's it. Yeah, Jane. She wants, no, no.
Okay, we are getting there, we're almost, we've got the core, kind of structure of a state machine here, right?
Slide.
We have code space for all our states, and we have code space for all our actions. We've defined them, we've talked through, we know what our actions, we expect of our actions,
Forward.
and we know
Then it is 0 to 10.
by drawing our diagram, what our transitions are to tell us what the next state should be and what the next action should be. That's what we keep caught up. Guys, need help, you're good?
Yeah, I got it.
Caught up? Alright, okay, so we're gonna do a little bit more kind of, tricks of the trade with case structures. So, we already have, so everybody go to where this code is written, go to this code space. You do that by, selecting the menu. Or you can hold down the control key and you can use your mouse wheel and it will scroll through each of the frames. We'll find this. Okay, so, some people's isn't gonna say increment, it's gonna say something else, right? So you can highlight the top here and delete it and just start typing increment. And it will try to find, it only has the options in that list, so it'll do kind of a lookup for you, and once you find it, you just off click. So make sure we'll make this case increment, right? And now we want a decrement case, okay? So instead of me being a lazy programmer, having to write all this code again, I'm going to copy this code, okay, and make it decrement. And just do a small change and make it decrement. So I'm gonna go, so watch first and then you guys do this. I'm gonna go to my decrement case and I'm gonna delete it. Delete this case. And then I'm gonna go to my increment case and I'm gonna say duplicate. Duplicate the code in this case. Okay? Now the only difference between increment and decrement is this +1. So I'm gonna replace the +1 with a -1. Right click, replace, numeric, -1. Decrement. Okay? And then no action does no action. Doesn't do anything to the data. Alright? So go ahead and do that. Create a decrement case that has the -1 in it.